Welcome to our discussion of Kw and pH. In this lesson, we're going to define Kw, define and identify the relationship between pH and pOH, perform calculations using Kw, pH, and pOH, and describe two methods of measuring pH. Let's begin with our discussion of Kw, which is the ionization constant of water. And to understand what that really means, we have to know a little bit more about water. So in addition to being amphoteric, meaning it can act as either an acid or a base, water can also auto-ionize, meaning that it automatically breaks into ions, hydrogen ions and hydroxide ions, as shown by this equation. However, this isn't exactly what happens because we rarely have a single water molecule breaking apart into ions. Most of the time, we're going to have lots of water molecules, and some of those are going to break apart into ions. So what's really going to happen is actually this equation, where we have two water molecules breaking apart into a hydroxide ion and a hydronium ion. So it's still breaking apart into hydroxide and a hydrogen ion, but that hydrogen ion isn't going to be free floating by itself. It's actually going to hook up with a water molecule and form hydronium, or H3O. So this H3O is really this hydrogen ion that is hooked up with a water molecule. Well, as you may have noticed, these reactions, this ionization of water, is actually a reversible reaction. And as a reversible reaction, it will reach equilibrium, and so it has an equilibrium constant, or Kw. So as with any other equilibrium constant, it's going to be equal to our concentration of our products over our concentration of reactants. But if you notice, our reactant, water, is a liquid, so it's actually going to be left out of our equilibrium expression. So our Kw is simply the concentration of our hydroxide ions times the concentration of our hydrogen ions, or the concentration of our hydronium ions, depending on how the equation is written. In order to find the value of Kw, then we need to know the concentration of our hydroxide and our hydrogen or hydronium ions. Well, the first thing we know is that the concentrations are actually going to be equal because they have a 1-to-1 mole ratio. And experimentally, we found that the concentration of both our hydroxide and our hydrogen or hydronium ions is 1 times 10 to the negative 7th. So when we multiply those together, our Kw turns out to be 1 times 10 to the negative 14. And this is going to be the same no matter what the temperature is. So for this equilibrium constant for Kw, temperature does not affect the value. The ionization of water being a reversible reaction also means that Le Chatelier's principle applies. So if the concentration of either product increases, the other must decrease, and vice versa, to keep Kw constant at 1 times 10 to the negative 14th. Let's take a look at an example of how to apply our newfound knowledge about Kw. So for example, what is the hydrogen ion concentration if 0.1 moles of hydrochloric acid dissolves in 10 liters of water? What is the hydroxide ion concentration? Well, first we need to write out our equation of HCl plus water is going to give us hydronium ions and chlorine ions. But since this is a bit cumbersome to write, we can actually simplify the equation. So it's just hydrochloric acid dissolving into hydrogen ions and chlorine ions. Because we know this is all taking place in water, so we can assume that water is present. But whether or not we write it in the equation isn't going to affect how we do the calculations. One thing to note, however, is that when we write it in this form, it's no longer a reversible reaction because we're just looking at the dissolution of hydrochloric acid, a strong acid. However, we can't forget that water is also auto-ionizing in this reaction as well, and that is what is going to allow us to use Kw. So as with any other problem in chemistry, always start with what you're given. So the question tells us that we have 0.1 moles of hydrochloric acid dissolved in 10 liters of water. So this means we have a molarity, or a concentration of hydrochloric acid, of 0.01 molar. And since it's a strong acid and dissociates completely, we know from our previous lesson that we're therefore also going to have 0.01 molar hydrogen ions and 0.01 molar chlorine ions after this dissociation. And we've already answered the first part of the question. The hydrogen ion concentration is equal to 0.01 molar. Well, the question also asks us to find the hydroxide ion concentration. Well, since we know that Kw equals the concentration of hydroxide ions times the concentration of hydrogen ions, and since Kw is equal to 1 times 10 to the negative 14, and our hydrogen ion concentration in this case is 0.01 molar, we can very easily calculate our hydroxide ion concentration. One last thing to notice about this example is that at the end we found that our concentration of hydrogen ions is greater than our concentration of our hydroxide ions, which is exactly what we would expect since we're working with an acid. Remember, in our last lesson, the Arrhenius definition said that an acidic solution has a higher concentration of hydrogen ions than hydroxide ions. A basic solution has a higher concentration of hydroxide ions than hydrogen ions, and that a neutral solution has an equal concentration of hydrogen and hydroxide ions. And that part of the Arrhenius definition still holds true and serves as a great double check while you're doing your calculations. If you're working with an acid, you should have a higher concentration of hydrogen ions, and if you're working with a base, you should have a higher concentration of hydroxide ions. Let's try one more example, but first try this one on your own. Pause the video, work it out, and then when you're ready, hit play to check your answers. Well, there you go. Hopefully your answer looks something similar to mine. So the first thing that we have to do is to write our equation. And remember, we can sort of take for granted the fact that this is happening in water and omit it from our equation. So we just have NaOH dissociating into its sodium and hydroxide ions. And they told us that we have 0.04 grams of NaOH dissolving in 1 liter of water. So we have to convert that from grams and liters into molarity. So we do that by using this equation here, our grams divided by our molar mass, and that'll give us our moles, and it's over 1 liter. So our moles over 1 liter is going to give us a concentration of 0.001 molar for our NaOH. But because we know this is a strong base, it's going to dissociate 100%, so our concentration of our ions are going to be exactly the same. So our concentration of our hydroxide ions is also going to be 0.001 molar. And then the second part of the question asks us to find our hydrogen ion concentration. Well, since we know our Kw equation and our Kw value, we can do that very easily by plugging our hydroxide ion concentration in here and then solving for our hydrogen ion concentration here, which gives us an answer, a final answer of 1 times 10 to the negative third. Now let's take a look at our next topic, pH and pOH. We identify substances as either acidic or basic, also known as alkaline, by their hydrogen ion concentration. And pH is a way of more easily expressing that concentration than using molarity, as our molarity is often a very small number and kind of cumbersome to work with. So pH actually stands for the power of hydrogen, and it refers to the exponent, or the raised power, of the molarity of our hydrogen ion concentrations. The pH scale is something most of you are probably familiar with already. It goes from 0 to 14. 7 is neutral. Anything above 7 is considered basic or alkaline, and anything below 7 is considered acidic. On the acidic side, we're going to have a higher concentration of hydrogen ions than hydroxide ions. On our basic side, we're going to have a higher concentration of hydroxide ions than hydrogen ions. And right at 7, where we're neutral, where our pH is neutral, we're going to have an equal concentration of hydroxide and hydrogen ions. So something really important to remember about the pH scale is that since we're working with exponents, it's a log scale, meaning that it increases by the power of 10. So that means that something with a pH of 6 is 10 times more acidic than something with a pH of 7. And something with a pH of 5 is 100 times more acidic than something with a pH of 7. There are several equations for you to use as you're calculating your pH and pOH. So your pH is equal to the negative log of your hydrogen ion concentration. Your pOH, which is the power of hydroxide, is equal to the negative log of your hydroxide concentration. To find your hydrogen ion concentration, you can take the antilog of your negative pH. And to find your hydroxide ion concentration, you can use the antilog of your negative pOH. And then our pH and our pOH will always add up to 14. So don't be put off or scared by these log functions. It's just plugging it into your calculator and letting your calculator do the heavy lifting for you. To enter the antilog into your calculator, all you need to do is hit the second button and then log. And that's how you can type in antilog for completing these calculations. So let's get some practice using our toolbox and doing some calculations. So we're going to fill in this table together. So let's do the first row. So in this row, they gave us our hydroxide ion concentration. Well, whatever they give you, you want to be on the right side of the equal sign for one of your equations. And the only place that we have the hydroxide ion concentration on the right side of the equal sign is right here. So we can really easily plug this value in for right here and find our pOH. And when we do that, we do pOH equals our negative log of 1 times 10 to the negative 7. And we find that our pOH is 7. So once we have our pOH, we look back up at our toolbox and see what else we can solve for. Well, down here, I notice that if I have my pOH, I can very easily find my pH. So pH plus 7 equals 14. So my pH must be 7. So now the only thing that I'm missing is my hydrogen ion concentration. Well, I can find my hydrogen ion concentration because it's the antilog of my negative pH. So in my calculator, I type second log negative 7, and I get a hydrogen ion concentration of 1 times 10 to the negative 7th. So let's try this next example together as well. So in this one, they only gave us the pOH. Well, I know that from down here, pOH plus pH equals 14. So our pH plus 8 equals 14. So our pH must be 6. Well, once again, now that I have my pH, I'm going to look for one of these equations that has pH on the right-hand side of the equal sign. And I find it right here, so I can easily find my hydrogen ion concentration. So in my calculator, I put second log negative 6, and that gives me a hydrogen ion concentration of 1 times 10 to the negative 6th. So now I have everything except my OH concentration. And something else I notice is that I have my hydrogen ion concentration, but I'm missing my hydroxide ion concentration. So another equation that we could add to our toolbox is our Kw. Because I know if I have my Kw and I have my hydrogen ion concentration, I can really easily find my hydroxide ion concentration. So using Kw, I plug that in. So 1 times 10 to the negative 14 equals 1 times 10 to the negative 6th times my hydroxide concentration. And when I calculate that out, I find my hydroxide concentration to be 1 times 10 to the negative 8th. So now try filling in the last 2 rows on your own. Pause the video, and when you're finished, hit play to reveal the answers. So there you go. I hope your answers match my answers, and I also hope that you noticed some patterns that emerged as we did these calculations. So if you take a look, our pH of 7 is the exponent of our hydrogen ion concentration, and our pOH of 7 is the exponent of our hydroxide ion concentration. And that pattern holds true for every single one of these calculations, which exemplifies why our pH and pOH are called the power of hydrogen and the power of hydroxide, because it's referring to these exponents. And as you can see, writing it as a pH with a single number or a pOH as a single number is much easier and much more efficient than using our molarity concentrations. So the last thing we want to be able to do with these numbers is classify them as either acidic, basic, or neutral. So for this one with a pH of 7, it's going to be a neutral solution. So remember, we're just looking at pH to classify as acidic, basic, or neutral. So 6, because it's less than 7, is going to be acidic. 3 is also less than 7, so it's also going to be acidic. And 12 is greater than 7, so it's going to be basic or alkaline. So in addition to using calculations, we can also measure pH in the lab. And there are 2 main ways in which we do this. The first of which is an indicator, which is a compound that can reversibly change color depending on the pH of the solution. These indicators include things like pH paper, litmus paper, or even cabbage juice, all of which are going to change color when they're introduced to solutions of varying acidity or alkalinity. The second, more technical way is with the use of a pH meter, which utilizes complex electrochemistry to measure accurate pH levels. Both methods, indicators and pH meters, have their value and are often used in combination for the best results. This concludes our discussion of KW, pH, and pOH. Bring any questions you have with you to class.